To really understand cellular transport, you have to first understand two of the basic laws of thermodynamics. The first law, known as the law of conservation of energy, states that energy can neither be created nor destroyed. It can only be transferred or changed from one form to another. For example, turning on a light would seem to produce energy, however, it is electrical energy that is converted. Energy cannot be produced by a cell, it can only be borrowed from someplace else. The second law of thermodynamics says that the entropy of any isolated system not in thermal equilibrium almost always increases. Isolated systems spontaneously go towards thermal equilibrium, the state of maximum entropy. Basically, the entropy of the world only increases and never decreases. A simple application of this is your room. If it's not cleaned and tidied, it will invariably become more messy and disorderly with time, regardless of how careful you are to keep it clean. When the room is cleaned, its entropy decreases, but the effort to clean it has resulted in an increase in entropy outside the room that exceeds the entropy loss. Plant and animal life maintain a high degree of organization only because it is being resupplied with energy from the sun. So diffusion is the spreading out of molecules across a cell membrane until they're equally concentrated. So if you look at diffusion, materials on the left are going to pass over to the right until they are balanced. Now, diffusion looks at solutes, not water. Do not get confused there. Now, it results from the random motion of molecules and occurs along the concentration gradient. You go from an area of high concentration to an area of low concentration. But substances diffuse separately. So I have purple and orange. Purple and orange are going to pass back and forth equally until you have the same amount of both on either side. But it doesn't matter like, oh, I have all purple on the left, oh, I have all orange on the right, but there's the same number, so it's okay. Diffusion doesn't care. Everything is separate. Now, when you actually watch this occurring, material flows from high to low. But once it's balanced, does it stop? No. There is no net flow. So there's a dynamic equilibrium. Materials going in and out equally. Now, small, uncharged, nonpolar substances will do this spontaneously, say, for example, CO2, but other things will need help. Some substances still use diffusion, but they're too big to pass through the membrane, so they use proteins instead. Large, charged, and polar substances are going to use these proteins to diffuse. This is still passive, no energy is necessary, it's still going to occur along the concentration gradient, but it's going to use a protein to help it. The two major examples that we're going to talk about are water, which uses the aquaporin protein, and glucose, which uses the glucose transporter 1 or GLUT1. So transport proteins provide access across the membrane. Each transport protein is specific to the substance that it will move. Glucose transport protein in the liver will carry glucose from the blood to the cytoplasm, but not fructose, which is a structural isomer. Some transport proteins have a hydrophilic channel that move certain ions through, simply providing corridors allowing its transport. And those are going to allow a very fast transport. An example of that is the aquaporin, which can allow thousands and thousands of water molecules through very, very quickly. So say, for example, your small intestines will need a lot of aquaporins. Osmosis is the diffusion of water molecules through a selectively permeable membrane from an area of greater concentration of water to an area of lesser concentration of water. So looking at the diagram on the right, we can see the water molecules moving from high to low. But if you look at the solute, it looks backwards from diffusion. It looks like it's going from low to high. Don't let that confuse you. Osmosis is about the movement of water, nothing else. So when you're looking at an osmosis question, you need to understand that unlike regular diffusion, it looks at all solutes equally. So a simple rule of thumb, if it's diffusion, everything is separate. If it's osmosis, everything is together. So be careful when you're trying to do that type of situation. Now, if you start osmosis with an equal amount of solute, water will move back and forth equally, a dynamic equilibrium. So it's not going to be favoring one side over the other. Just looks at the concentration of solutes. Now, tonicity is a measure of the effective osmotic pressure gradient, where the water is going to go. It is always going to be a comparison. You cannot have, oh, this cell is hypertonic. No, it has to be hypertonic compared to something. So if a cell is in a hypertonic solution, as in the top picture, this solution has more material outside than there is inside. So there's more solute and less water. So water is going to go out of the cell. Okay, in an animal cell, it's going to cause it to shrivel, or the real word crenate. And in a plant cell, it will cause it to plasmolyze, which is when the cell membrane literally tears away from the cell wall. In an isotonic solution, the material is equal. Okay, so equal amounts of solute and water. Material will go back and forth equally. In plant cells, this will make it wilt. But in animal cells, this is our normal condition. This is the preferred condition. In a hypotonic solution, the solution has much less than the cell. So there's less solute, more water. So water will come in. That does mean that in animal cells, the cell will swell. And if you stay in this kind of situation, it could eventually lyse, which is when a cell bursts. But that's an extreme. Plant cells like this. They have a cell wall, so they're able to fight against this pressure. That means that they're going to become turgid, very stiff and rigid. That crisp celery is going to be turgid, and that is the normal preferred condition for plants. Looking at this from a diffusion perspective, sucrose is higher inside the cell than outside, as is glucose, and there is no fructose at all. So if this was a diffusion question and everything could pass, well, fructose is going to go in and glucose and sucrose are going to come out. But what if the membrane is semi-permeable? What if these materials cannot be exchanged? Well, that's where osmosis comes in. So it goes from high to low water, but it looks at the materials as totals. So inside the cell, I have 0.05 molar, and inside the solution, I have 0.03 molar. So the cell compared to the beaker is hypertonic. It has more solutes. But the beaker is hypotonic. It has less solutes. So you go from more water to less water, or less solute to more water. So which way does the water flow? In. Water will flow in, from less to more solute, or from high to low water. A few last points I want to make sure you remember. Cell survival depends upon balancing water uptake and loss. So osmosis is extremely important to our homeostasis. Now, plant cells are going to prefer hypotonic environment because that pressure on their cell walls allows them to stand upright. But animal cells are going to prefer isotonic environments. You can see the red blood cells on the right here. Water must come in and out to balance that water. So it's very essential to remember which one is preferred for which type of organism.